Okay, so we next introduce the concept of correlation coefficients of two random variables, which are non-constant with v1. Okay, because if either x or y is constant, then its variance would be equal to 0. Okay. All right, and so the correlation coefficients will be denoted as rho of xy. Okay. So it's defined as here, rho xy is defined to be the ratio of covariance of x and y, and the square root of the product of variance of x and the variance of y. Okay, so this is the reason why we require that both x and y are non-constant. Okay, so if they are non-constant, then by proposition 7.4.c, that these two variants are non-zero. Okay, so we can put this product in the denominator. Okay, so which are non-constant with v1 if only variance of x and the variance of y will be greater than 0 by proposition 7.4.c. Okay, so we have the definition. All right, and by proposition 7.4.g, we prove last Thursday. Okay, we have proposition 7.4.g is another version of Schwarz inequality in terms of covariance. Okay, so we know that in this proposition, we know the square of the covariance is less than equal to the product of the variance of x and variance of y. So that we have covariance. So we have this one. We know this is okay, and if you take the square root, so you have that covariance of as less than or equal to the square root of variance of x and the variance of y. Okay, and so this is saying that covariance of xy divided by the square root variance of x, variance of y is less than or equal to 1. Okay, and so this is implies that if and only if that the covariance of x and y is in between 1 and minus 1. The correlation coefficient, I'm sorry. So the correlation coefficients of x and y is in between minus 1 and plus 1. Any questions? So now, proposition 7.4.h for two random variables x and y, which are non-constant with probability 1 and have finite second moment. Then we have 1, the correlation coefficients of x and y is equal to 1 if and only if y is equal to alpha x plus delta with probability 1 for some constants alpha, which is positive, and the delta is in R. Okay? So if the correlation coefficients between x and y is equal to 1, then y is a linear function of x with the leading coefficient alpha, which is positive. So they have positive correlation. Okay. Second, if the correlation coefficient is -1, then if and only if y is equal to alpha x plus delta with probability 1 for some constants alpha, which is negative, but delta can be an arbitrary real number. Okay. Okay, so if the correlation coefficient is equal to -1, then y and x are related, it's negatively related linearly with respect to 1. Okay, with respect to 1. Okay. So that in many tests of two random variables to see if they are linearly related, okay, we usually compute the correlation coefficients between these two random variables. And if the absolute value of the correlation coefficient very close to 1, so for example, 0.95, 0.96, etc., then we strongly believe that they are linearly related. Okay, either positively linear related or negatively linear related, dependent on the sign of their correlation coefficient. Okay, so that and here we have exact expression with probability 1 linearly when we have these two conditions. Okay. In linear algebra, you learn how to use this square test, right? To fit the two random data. Okay, so that if the mean square error is quite small, then you will see that they can be say that these two variables x and y are linearly related. Okay, and so you will find a so-called regression line. Okay, so this line is actually the linear relations to approximately related to random variables. Okay. So here is the statistical statement about such kind of estimation. Okay, so the proof here. Okay, so from the discussion in above, okay, we know that rho xy, okay, so rho xy equal to plus 1 minus 1, if and only if y is equal to alpha x plus theta with probability 1 for some constants alpha, delta in R. Okay? Right? By proposition 7.4.2. Okay. So we know that the inequality becomes to equality if and only if that y is equal to this one. Now, so since y is non-constant with probability 1, alpha must be non-zero. Okay, because if alpha is 0, then y is 0 with probability 1. Okay, which is a contradiction. So we have this one. Okay, but now we compute, in this case, the correlation coefficient okay, so we have the covariance of x and alpha x plus gamma plus delta, and the variance of x times variance of alpha x plus delta. Okay. Now, from a theorem about variance and covariance in, I think, okay, in proposition 7.4.2. So we know this is actually equal to covariance of x, alpha x, square root variance of x times variance of alpha x. Okay, so the constant term, does not contribute anything. Okay, so you can remove them, and so this is alpha x. Okay, all right, and here we have variance of x and the alpha square variance of x. Okay, so both of them, this is by proposition 7.4.2. Okay, so we have that. Okay, and so this is alpha and the square root of alpha. Okay, so that this is plus 1, if and only if alpha minus 1, and we have done. Okay, so if alpha is positive, if only if the correlation coefficient is positive 1, if alpha is negative, then the correlation coefficient is -1. Okay. Okay, so this is exactly we have here. Any questions? So now we can say the correlation coefficient rho of xy is a measure of degree of linearity between two non-constant occurs with probability 1 random variables. And a value of the correlation coefficient near +1 or -1 indicates that a high degree of linearity between x and y. Okay. Whereas a value near 0 indicates that such linearity is absent. Okay, so that the other implication is that a positive value of rho xy indicates that y tends to increase when x does, whereas a negative value indicate that y tends to decrease when x increases. Now, a definition is that if the correlation coefficient is 0, then x and y are called uncorrelated. Okay, uncorrelated. All right, and so if x and y are independent, then then we have the expectation of their product is equal to the product of their expectations. So that the covariance between x and y, which as we computed, it's 0. And then the correlation coefficients between them is 0. Okay? i.e. x and y are uncorrelated. Okay, so independence between two random values implies that these two random variables are uncorrelated. Okay. Any questions?
Just like expected value is the average of the sample, what is the physical significance of correlation? What does it tell about?
So that, all right, so the implications here, extreme case, if the correlation coefficients has extreme values here, so this proposition gives us, because we know correlation coefficients between -1 and 1, right? So that is from the theory. And so if they happen to be these two extreme values, then they are linearly related with probability 1, which means that in probability theory, they are exactly, I mean, because probability 1 means that it happened 100%, right? Yeah. So, and that these two random variables, because they are random variables, but they are linearly related. As we know, x is a function, right, on the sample space. Y is also a function. So these two functions are linearly related. Okay. This kind of relationship is highly demanded in many different disciplines. For example, in medicine societies, if a drug company wants to investigate the effectiveness of a drug, so they will give a group of patients with different doses of the drug, and so X is the dose of the drug, and the Y is the effectiveness of this drug. Like for example, if the drug is for cancer, okay, so that Y would be the survival time of cancer patients, okay, and so that they will see the amount of drug, for example, the length of given the drug delivery, for example, right? If they have, for example, if they have a positive relationship, so if this is the one and the alpha is positive, then the drug company will claim that this drug is very effective for a certain cancer. Okay, and the FDA in the United States may approve that the drug to the market so that the drug company can make money. But if the correlation coefficient is 0, suppose that, then basically this means statistically this drug is not effective.
What if it's negative?
Statistically.
And if it is negative, what is that? It's
No. If negativity, then that is worse, right? that should be abandoned, right? Okay. Well, that means that a patient take drugs and will shorten their lifetime. That is negative effect. That it would be called it's called the poison, right? It's not a drug. Okay. Because there are many factors to affect the effectiveness of the drug, right? Many different conditions. It's not hard to find a functions for that. A deterministic function, very hard, if not possible. Okay, it may take 1,000 years or 10,000 years, but any company cannot afford it, right? So they should have a result in the short, maybe several years, right? In before, maybe that would take 10 years for that. Okay, so that's why drug in dealing with cancer are very expensive. Yeah, because they take a long time to determine some statistical results and to persuade the FDA in the United States or other food and drug agency in Europe, maybe in India, in China, Taiwan, Korea, Japan, right? Their agencies in different countries to approve the drug so that they can make money. Okay. And the statistical test, statistical argument will be a very well acceptable argument in the medicine society. Okay. So the implication here give you the picture about how to use the computation of correlation coefficients. Okay, so a positive value indicate that they tend to, so positive value will be good. And so how big with the alpha is actually, if the positivity is significant or not, then you have to use statistical method, the testing method to do that. So statistics is a very good subject to study, but this is statistics. This subject it's based on the theory of probability. Okay, so you have to understand the theory of probability before you understand statistical results. Okay, because they tends to be complicated if you subject to different tests. Okay. But this course gives you a solid foundations, okay, to understand further study of statistical results. Okay, so you see, we have built up a lot of basic concepts in these sections, and the final result terms appealing, right? Because they will give us the applications. Okay, to different disciplines. So any further questions? Okay, so if no, then we'll go to the central parts of this chapter. It's about conditional expectation. So in this section, we will take a quite different point of view of conditional probability, conditional distributions, and with that, we can compute conditional expectations. Okay, as you will see. So you're welcome to raise your hands if you encounter any confusion. Okay, in these sections. Okay. All right. So we consider discrete case first, because they are very concrete. Okay, so we recall some material we learned in chapter 6, because in chapter 6 we learned conditional distributions. Okay? So the conditional PMF, probability mass function of random variable x, given that random variable y is equal to little y. And so this conditional PMF is defined in this way. As we know, that is equal to, okay? And so this is actually so if the marginal PMF of random variable y is positive at little y, then this conditional PMF is this ratio. And the numerator is the joint PMF of x and y, as we know in chapter 6. And if the marginal PMF of y is equal to 0, okay, then the conditional PMF of x given random variable y equal to little y is defined to be the unconditional PMF of x. Okay. Right. And this is for all x in R. Okay. Right, so this is what we defined in chapter 6. Okay, so based on conditional PMF, so the conditional, we know conditional PMF has property like a PMF, okay, of a random variable, so that the conditional expectation of x given that random variable y is equal to little y is defined as here the conditional. All right, so this is the conditional expectation of random variable x given that random variable y is equal to little y, which is defined to be the summation over x for all x, and okay, so it's this sum. Okay, so this is defined in terms of the conditional PMF. Okay, and it has two expressions. Divided by, and the other x, which is if provided that the sum exists. Okay. We understand the summation, even though we say over all x, which means that which is equal to so we understand that. So this is actually okay, with AI possible values of x. Because x is discrete, so it has, at most, it has countable many possible values. So that the index is, capital I is the countable index, say, right? So that this summation actually is this summation, okay? But we understand that the writing, this one is very suggestive, okay? And it avoids to every time to mention that A sub I are possible values of random variable x, okay? Right? And so that the same, this one is actually on the summation okay, and this is sum x equal to okay, same. Okay, so provided the sum exists, so you can evaluate the sum. You can evaluate the sum. Okay. So the definition of conditional expectation of a discrete random variable x given a discrete number y has a specific value d to y is defined in terms of the condition of PMF. Okay. Now, a special case, if x and y okay, are independent, okay, then we have the conditional PMF is equal to the unconditional PMF of x. Okay, for all x, y in R. All right, so conditional PMS is a function of x and y, and x and y can be any real numbers in R. Okay, and equal to this function. Okay, so the equality is true for all x, y in R. This is by proposition 6.4.b. All right, so prove this result before in chapter 6. And then, so in this case, when the case is that x and y are independent, then if we compute the conditional expectation of random variable x given that random variable y equal to d to y, by our definition, we know this is, and now you have, this is 1. All right, so you can see it's a constant, all right, which is just the unconditional expectation of random variable x. So this is for all y. So that, all right, so this is for y. Provided that the expectation of x exists. Okay. So this is a special case. Right? This is a special case. All right. So now if the conditional expectation E of x given y of x given random variable y equal to y, if the conditional expectation exists and is finite for all y in R, right? So if this is the case, which means that we can evaluate all the sums, right? And all these sums are finite for every y for every real number y. Okay. Then we can define. So we can define a real value function on R as here. So we define g of y okay, so we can use because for each y this value exists and is finite. Okay, so we can use this to define a function g. All right, and then the function. So the function or the signal processing function g of y, okay, is a discrete random variable, okay, by a proposition in chapter 4. Okay, I forgot that, but you can find it. Okay, so and it's called a version of the conditional expectation of x given y. Okay, so given y, so given random variables. Okay, denoted as expectation of x given y. Okay, so this notation is a function of y. Okay, so this is in here, and for an outcome omega in the sample space, we have that omega. Okay, so this is actually okay. So this conditional expectation of x given y is a function of y, which is equal to gy. Okay, and so this is the g of y omega. Okay, but by definition, so this is expectation of x given y equal to y omega. So why we call this random variable, this function of y, this random variable, by this one? Because G contains what? The conditional expectation of x given y equal to a specific value. Okay. Okay, so this function, this G function, contains all the information about conditional expectation of x given that this y is equal to a specific value. Okay. And by the construction, this has become to a discrete random variable. Okay, and so the reason, that because it's a function y, so that's why we use this notation here. So the expectation of x given random variable y, this is a random variable. Okay, because it's a function of y, so that this is a discrete random variable. And if you want to evaluate the value of this random variable at a certain outcome, then you apply here. This is exactly equal to the conditional expectation of random variable x, given that the random variable y equal to a specific value. And this specific value is actually the value of random variable y at this outcome, omega. And you will see this construction of the so-called conditional expectation of x given another random variable. All right, this definition or this construction will be very useful, okay, in many disciplines. Mathematics, engineering, economics, finance, a lot of places, okay. You will use this construction. Okay, so we turn, because conditional expectation here, this is a value, right? It's a real number. But by using this construction, the concept becomes to a random variable. Okay, so this is a very, very important construction or concept built in probability theory. Okay, I can say that it is very important, very, very important. Okay, so but in here you know that how to evaluate it. Any questions? Okay. And since it's a discrete random variable, right? So now by proposition 4.4.1, okay, the expectation of this random variable, the conditional expectation of random variable x given random variable y, is here. Okay, it's actually, okay, by its definition, it's expectation of g of y. And because this is a function of y, so that this is okay. And so this is y, and right, and provided that the sum exists. Okay. So if the sum exists, we can compute the expectation of this random variable. Okay. Right. So you see here. So the computation depends on what? Depends on the marginal PMF of y. PMF of y. Okay. And also depends on the conditional expectation of random variable x, given that random variable y has a specific value y. Okay. Now the next theorem summarize important results. So proposition 7.5.1 discrete case. So it's a theorem, a part of theorem in textbook, but the statement in the textbook is not precise. So please see the statement here. So let x and y be two discrete random variables. Okay. If x has a finite expectation, okay, so if x has finite expectation, then the conditional expectation of random variable x, given that random variable y is equal to little y, exists and is finite for all y in R. Okay, so this is a sufficient condition that to guarantee that for all y in R, this conditional expectation of random variable x, given that random variable y equal to little y exists and is finite. Okay, and this random variable constructed, so a version of the conditional expectation of random variable x given random variable y has a finite expectation too, which means that the sum exists. Okay, the sum exists and is finite. All right, so this has a finite expectation with what? So its expectation is equal to the unconditional expectation of x. Okay, so so this identity is very important. If we know that random variable x has a finite expectation, but it's very hard to evaluate. It's very hard to evaluate this expectation directly by using the formula. So we know we can right? So that right? So we can evaluate this sum, but it may be very difficult. Right? Maybe very difficult to find them. For example, it's very difficult to find the marginal PMF of x, for example. Maybe it's very difficult. All right?
For real cases.
Yeah, for many real cases. Okay? So the PMF of x is very hard to find them. Okay? So this one provided a normative way, an indirect way. So this way is what? Is to find a version of the conditional expectation of random variable x given that y equal to random variable y. And y is a property selected sign information. Okay? Because if you have a sign information y, then from y, it's very easy to know x. This is quite often happen in realities, okay? So that you will be able to find this one easier than the job to find this one. And also it's much more easier to find the probability mass function of this sign information y. Okay? So you know that this is easy. This is also easy. So you can compute this expectation. So you know this expectation, and this expectation is equal to the expectation of x. Okay? So it gives you indirect way. All right? And the selection of y depends on your genius in the investigation. If you have insight about the problem, you may be possible to find a sign information y. It depends on you, right? Different researchers, different engineers, may have a different perspective, right? So may find different y. A clever one, a clever choice is a y such as this is easy to compute, this is easy to compute. Okay? This is easy to compute. And then you can compute this is sum. All right. So this proposition actually is very important in applications. Okay. And the theorem here, I state here, give you the only sufficient condition is that x has a finite expectation. Okay? So once x has a finite expectation, then this is guaranteed. Because everything here is if, right? There are a lot of conditions. Okay? So if x has a finite expectation, then that for each y, for each real number y, this number, this is expectation, exists as finite. Okay? So g of y is well defined, and so this is a discrete random variable. And it also guarantees that this random variable has a finite expectation, and its expectation is exactly equal to the expectation of x. Okay, so you compute the expectation of x in 2 steps. This is the first step, and this is the second steps. Okay. Okay, any questions before I give a proof? Okay, so let's take a break to 2:35. Okay. So before proving proposition 7.5.1.d, okay, we need a theorem on iterative series. Okay. So theorem all right, so let I and j be two countable index say. So let Fij be a real valued function on the pair in the Cartesian product. Okay? If the summation of j, okay, is finite for all I, and the summation of I okay is also finite. So if we have these conditions, then all right, one, the double sum if so the summation that the double summation converge. So the double series, I have to say, the double series converges absolutely. Second, the series I in I, Fij converges absolutely for all j in j. And three, maybe I will see the two series summation Oh, this one, okay. Because this already says that the summation over J converges absolutely. So that's fine. I just need to, okay, converges absolutely for all J in J. And summation okay, converges absolutely. And third one, the double series can be evaluated in two ways. Or okay. So we can exchange the order of summation. So to guarantee the exchange of summation, we need these sufficient conditions. Okay? This is sufficient condition. All right, so proof. Position 7.5.1.d. Before the proof, please let me know if you have any question about the statement of this theorem on iterative series. Okay. If you want to have a reference for this theorem, well, you can please see Pastor's book on mathematical analysis. I recommend the second edition. Okay. And specifically on theorem 8.43 on pages 202 up to 203. Okay. Right. Okay, but if you are satisfied, you just take this theorem as for granted, okay, and use them. But this is very important because actually, when we consider the discrete random variables, we a lot of time use these theorems to deal with the iterative series. Okay. right, so this gives you the condition that you can exchange the order of summation. Okay, and the sufficient condition is here. Okay, is that. Okay, so now we'll give a proof of that. All right, so let AI and the BJ, okay, be the sets of possible values of x and y respectively. Where I and x, I and j are countable index sets. And we know that x has a finite expectation if and only if the expectation of the absolute value of x is finite. Okay. Okay, so we know that the expectation is finite. Also, know that the joint PMF of x and y is equal to the marginal PMF of y times the conditional PMF of random variable x given random variable y at d2y. Okay, and this identity is true for all x, y in R. All right, so this is by proposition 6.4.a. Okay, so we know that. So we have this identity. Now, things. So we deal with AI times P y bj and the P x y AI given bj. Okay. All right. So we look at this one, and so we define this product to be our f of ij. Okay, in the theorem. So you can say it depends on the index. The index is I and the index I and index j here, right? And we sum over, we take the absolute value and we sum over index j. So here, so we know this is AI because the summation is over j. So I is independent of j, so we can take out AI and summation j in j. Okay, and because the probabilities are non-negative, so we have P, Y, Bj, and P, Bj here. But as we know by proposition 6.4.8, we know that this is, so that this is j in j, but this product is the joint PMF of x and y, right? At AI and bj. Now, when you sum over of all the j, we know this is just the marginal PMF, right? This is the marginal PMF we have. Okay, when we discussed in chapter 6, so we have this one. Okay, so we have that. And of course, this is finite for all I in I, right? So we check the first condition. Yeah. Okay? So we check. So this is finite. And we check the second one. Okay, and the AI. Okay, so again, this is Fij. Now, because the inner sum is the same as this one, so we know this is equal to, and the AI, and the PXAI here. Okay. Now this is actually X. Okay? So it is the expectation of X, of the absolute value of X here. And we know this is finite. Okay? So we check the condition already, right? The condition already. Is that okay? See here? This is what we have. Okay, and so by the iterative series, by the iterative series theorem, we have, okay, so now we just take what we need. One, so we have one that summation okay, so this we know this is f of ij converges absolutely for all j. Okay, so this is from here. Okay, and summation converges absolutely So first, the second, and we know that the summation is equal to, if we change the order of integration of summation, sorry. Okay, so we have that, these two implications. Okay, so we have these two implications by 2 and 3 in the iterative. Oh, I have already know that, so we don't need to say again. Okay. Now, for any y in R, so now we want to prove that this quantity, the conditional expectation of random variable x given random variable y equal to a specific value little y exists and is finite for all y in R. So we first consider y in R with such that this marginal PMF is positive. Okay. Then there is a j in the index say such that y is equal to bj, right? Which means that this y is one of the possible values. Okay, this means that it's one of the possible values, and so expectation of x. Okay, this one. So this is x. Okay. And this is equal to AI P AI given BJ. Okay, this is sum. But we know this sum converges absolutely. So this is sum. But what is this sum? This is sum. Okay, maybe I wrote here. Okay. Now this is sum. Right. So look at here, and this vector, the marginal PMF of y at B sub j is independent of the index I. So we have P okay, right? So that this summation is this vector times this is series sum. And because this product converges absolutely, so that which implies that the series sum converges absolutely. Okay? So that this sum converges which converges absolutely So this is implies that exists and is finite. Okay? All right. And for any y in R with P, the marginal P at little y is 0, then we know that this is equal to, okay, which is already, exists and is finite, which exists and it's finite already. Okay? Because by our assumption, X has a finite expectation, which means that this expectation exists as finite. Okay, so you combine them, so we conclude that this quantity, this conditional expectation of random variable X, given that random variable Y is equal to little y. All right, so this quantity exists and is finite. For all y in R. Okay, and then E, okay, and this one is real valued, or it's a discrete random variable. Okay. With expectation. Okay, so with expectation, so we compute. And we know this is equal to okay. So the expectation is this is summation, right? This is summation. Okay? So that this is, so we will have okay, and okay, in here. Okay, and so we will see okay. Now we turn the sum into series sum. Okay, so this is the iterative series sum we have. And now we can exchange the order of summation. Okay, this is equal to, so we can sum over J first. Okay, and this is AI here, and this here. So this is from okay in here. So so you can see this is summation I, AI. But as we know that this is the joint PMF of X and Y. Okay, and sum over J, you get PXAI, and this is expectation of X, and we have done. Okay. So this proposition tells us that we can compute the expectation of a random variable by conditioning. Okay, and the conditioning random variable y can be chosen as you wish. Okay, can be chosen as you wish. Yeah. Okay. Okay, so we finished the discrete case. Then can we do so for absolutely continuous random variables for jointly, I forgot, for jointly absolutely continuous random variables. So you have the big question here. Okay. All right, and the answer is yes. Okay, so it's very positive. We can do so. But we will state the main result like this result. All right, so we need a version of this proposition for joint to the absolute continuous case. Okay. So consider two jointly absolutely continuous random variables x and y with a joint PDF f of xy. Then we define two functions as before, as in chapter 6. are marginal PDFs of X and Y respectively. Okay? So we will use these two marginal PDFs defined this way. Okay? We know that. Okay, so recall a conditional in chapter 6, we define conditional PDF of random variable X given that random variable Y is equal to a specific value, little y, is defined as here. So that is, we separate them into two cases. So if the marginal PDF of random variable Y is positive at delta Y, then this conditional PDF will be this ratio. Okay? But if this value is 0, then we define the conditional PDF to be unconditional one. Okay? Okay, so this is our definition in chapter 6. Okay, and so I will stop here. So with this one, then we will define conditional expectation of random variable X given that random variable Y is equal to delta Y. Okay, and then we will try to find a version, okay, of this proposition for the joint to the absolute continuous cases. Okay, so I'll stop here and see you on Thursday.